Space holds a secret it does not want us to know. We celebrate the rockets and the bravery, the iconic images and the giant leaps. But behind these triumphs of engineering lies a shadow, a deeper layer of overlooked and underestimated perils. The immediate dangers of launch and the void of vacuum are just the beginning. For the dream of long-term missions, for planting flags on distant worlds and calling them home, we must confront a hidden catalogue of threats. These are not mere obstacles, but biological, psychological, engineering, and cosmic dangers that could silently undermine everything. By the end of this exploration, you will understand the 30 specific, hidden dangers that could be the true limiting factors for our future among the stars. What unseen force could erode an astronaut's mind millions of miles from home? What common element of every spacecraft creates a perfect breeding ground for catastrophe? The journey into space is the greatest adventure we can undertake, but are we truly prepared for the price the universe may demand? Our planet is a fortress we rarely think about. A thin blanket of atmosphere and a powerful magnetic field work together to shield every living thing from a relentless cosmic bombardment. The moment we leave that protective bubble, we are exposed. This is not the gentle warmth of sunlight, but a hail of atomic shrapnel moving at nearly the speed of light. It is called cosmic radiation, and it is the first, most pervasive hidden danger on our list. There are two primary sources. The first is from our own sun, in bursts of fury known as solar particle events. These are storms of protons that can deliver a lethal dose in hours if an astronaut is caught without sufficient shielding. The second, more constant source are galactic cosmic rays. These are nuclei of atoms from hydrogen to iron that have been accelerated across the universe by exploding stars. They are far more energetic and penetrating than anything from our sun. Think of it like this: on Earth, you might worry about a single bullet. In deep space, you are standing in a silent, invisible shotgun blast that never stops. The particles are so small and so fast they pass right through the hull of a spacecraft and right through human tissue. As they travel, they smash into the atoms of your cells, breaking DNA strands and creating a cascade of damaging secondary particles. The most well-understood long-term risk is a significantly increased chance of developing serious illness later in life. But for a mission to Mars taking years, there is a more immediate and unsettling threat. Research suggests this radiation does not just damage the body, it may directly attack the brain. Studies on animals show that exposure to similar high-energy particles can degrade the connections between brain cells, leading to measurable declines in memory, learning, and decision-making. Imagine halfway to Mars, the commander of the mission begins to struggle with focus or forgets critical procedures. This is not a story of sudden sickness, but of a slow, silent erosion of the very mind needed to complete the journey. We have built ships to withstand vacuum and temperature extremes, but crafting a shield against this subatomic hailstorm remains one of our greatest engineering puzzles. That silent assault on the brain is just one facet of a body utterly out of its element. While radiation chips away at our cells from the inside, another force reshapes the entire human form from the outside. We call it microgravity, but that term sounds almost gentle. The reality is a profound biological deception, a state where the constant pull of Earth that shaped our evolution simply vanishes. We know about muscle atrophy and bone loss, the body efficiently shedding what it no longer thinks it needs. Yet these are merely the most visible symptoms of a deeper systemic rebellion. Without gravity to anchor them, bodily fluids begin a slow migration upward toward the head. This cephalad fluid shift is not a minor inconvenience. It creates a persistent pressure inside the skull, a feeling of constant congestion that never clears. Over weeks and months, this pressure pushes against the backs of the eyes, actually flattening the eyeball and swelling the optic nerve. Astronauts return to Earth with changed vision, sometimes permanently. This condition, spaceflight-associated neuroocular syndrome, reveals a terrifying truth. The very architecture of our senses can be warped by the environment of space. Meanwhile, the cardiovascular system grows lazy. The heart does not have to work as hard to pump blood upward, so it weakens. The blood vessels lose their tone. The entire system adapts to a world without up or down. This is the hidden trap. Upon return to Earth, gravity reasserts its command. Now, that weakened system must fight to push blood back to the brain against a force it has all but forgotten. The result is orthostatic intolerance, a dizzying, fainting inability to simply stand up. The body's own regulatory mechanisms fail. These are not simple adaptations like building a callus. They are degenerative changes, a literal unraveling of the biological blueprint that has kept us alive on this planet for millennia. The human body, it seems, is not just visiting an alien environment, it is being quietly, systematically unmade by it. The body's silent rebellion is only half the battle. Within the cramped metal walls of a spacecraft, a different kind of danger takes root, one that preys not on bones and blood but on the human mind itself. This is the profound challenge of psychological isolation and confinement. Imagine a journey to Mars, a voyage lasting over 200 days one way. You are sealed inside a volume smaller than a modest apartment with the same handful of people. Outside your window is not a changing landscape, but an infinite, unchanging blackness. Earth shrinks from a vibrant marble to a faint, pale star, and with it fades the most powerful psychological tether in human history, the sight of home. In this environment, a unique form of mental strain emerges, sometimes called asthenization. It is not a dramatic breakdown, but a slow, creeping erosion of will. Motivation drains away, simple tasks feel overwhelmingly difficult. A deep emotional flatness sets in where nothing sparks joy or curiosity, not even the awe of floating above a distant world. The mind, deprived of natural sensory variety and social novelty, begins to turn inward in unhealthy ways. The greatest threat, however, may not come from within a single individual, but from the volatile chemistry between them. In such a small, sealed group, there is no escape from interpersonal friction. A minor habit, a tone of voice, a perceived slight, can fester and magnify over months into a deep resentment. On Earth, you can walk away, find space, talk to other friends. In a spacecraft, there is nowhere to go. The crew becomes both your only family and your only audience, a pressure cooker for conflict. Historical missions in analog environments on Earth have shown that without careful psychological support and crew selection, these tensions can sabotage teamwork and decision-making. The most haunting risk is the onset of a deeper mental health challenge, a severe depression or a break from reality when the immense distance truly sinks in. The realization is absolute. If something goes critically wrong with your mind or your relationships, no one is coming to help. Rescue is a physical impossibility. This transforms the spacecraft from a vessel of exploration into a gilded cage, where the walls are not just metal, but the limits of human resilience. The universe outside may be silent, but the one inside the helmet can become unbearably loud. While the mind contends with its own silent battles, the ship itself faces a more tangible and violent threat. Orbiting our planet is not a pristine void, but a cluttered junkyard moving at impossible speeds. Since the dawn of the space age, we have littered Earth's orbit with the ghosts of our ambition, spent rocket stages, dead satellites, and countless fragments from explosions and collisions. This is the hidden shooting gallery of low Earth orbit, where the primary danger comes not from distant stars, but from our own discarded technology. Each piece, from a lost bolt to an entire bus-sized satellite, is a hypervelocity projectile. In orbit, speed is everything. Objects travel at roughly 17,500 miles per hour. At that velocity, a fleck of paint no larger than a grain of sand strikes with the kinetic energy of a bowling ball dropped from a several-story building. A marble-sized piece of metal hits with the force of a hand grenade. For astronauts aboard the International Space Station, this is not a theoretical risk. The station's modules are peppered with tiny impact craters, and crews routinely perform emergency maneuvers to dodge larger tracked objects. The windows on the cupola observatory are replaced regularly because they become pitted and clouded by these microscopic impacts. Every mission must fly through this field of silent shrapnel, trusting that millimeter-thick hulls and Whipple shields, which are designed to vaporize small particles on impact, will be enough. But the true hidden danger is not a single piece of debris, it is the potential for a chain reaction. This scenario has a name: Kessler syndrome. Imagine if a collision between two large objects, like a defunct satellite and an old rocket body, shatters them into thousands of new fragments. Those fragments, now on new and unpredictable paths, then collide with other objects, creating more debris in an exponentially growing cascade. One collision begets 10, which begets 100. Within a short period, a shell of space around our planet could become so densely packed with whirling metal that it is effectively impassable. Satellites providing global communications, weather forecasting, and navigation would be shredded. Launching anything new, including crewed missions, would become an act of extreme recklessness. Low Earth orbit, the very highway to the cosmos, could be closed for generations by a single catastrophic event. This transforms the debris field from a nuisance into a slow-motion environmental disaster, one where every new launch adds to the problem and every piece of forgotten junk holds the potential to trigger a final, silencing avalanche. The greatest threat to our future in space may ultimately be the ghostly remains of our past, but the dangers we carry with us extend beyond the ship's hull. When we finally step onto another world, we will be greeted by a substance that seems deceptively familiar: moon dust. Scientists call it regolith, the layer of broken rock and dust that blankets the lunar surface. This is not the soft, weathered soil of Earth. It is a product of an airless world, constantly bombarded by micrometeoroids over billions of years. Without wind or water to smooth its edges, each tiny particle is a jagged, glass-like shard. It is also electrostatically charged by the relentless solar wind, causing it to cling to everything with a strange, stubborn tenacity. Apollo astronauts found it coated their suits, clogged equipment, and was tracked back into the lunar module where it smelled, they reported, like spent gunpowder. The immediate problem is its abrasiveness. This dust is so sharp it can grind away at the seals of spacesuit joints, compromising their integrity. It can scratch helmet visors to obscurity and wear down mechanical parts with alarming speed. For a long-term lunar base, this pervasive grit would be a constant, grinding enemy of any moving part. Yet the more insidious threat lies in what happens if it gets inside. Inhaling this jagged lunar dust would be catastrophic for human lungs. On Earth, miners face a condition called silicosis from inhaling crystalline silica dust, which scars lung tissue and makes breathing difficult. Lunar regolith is far worse. Its particles are sharper and more reactive. In the confined environment of a habitat stirred up by daily activity, this dust could pose a serious, long-term health risk with every breath taken. And if we look to Mars, the dust there presents its own unique nightmare. Martian soil is now known to contain significant amounts of perchlorates, chemicals that are highly toxic to the human thyroid gland. These salts also become reactive in the presence of radiation. For explorers on Mars, the dust is not just an abrasive nuisance, it is a poisonous, perhaps even corrosive contaminant. It would coat every surface, cling to every spacesuit, and without a foolproof decontamination process, it would inevitably find its way into living quarters and life support systems. The first footstep on another world may leave a permanent imprint, but that world will leave its own indelible and potentially lethal mark on everything we bring there. Even the most robust human body carries dormant passengers, viruses that have been with us for life. On Earth, our immune system keeps them in a permanent state of hibernation. In space, that delicate truce begins to break down. Research reveals a disturbing double blow. The body's defenses weaken just as its old adversaries awaken. The constant stress of confinement, the strange fluid shifts, and the very absence of gravity appear to send confusing signals to the immune system. Key defender cells like T cells and natural killer cells become less vigilant and less effective. They struggle to identify threats and mount a proper response, as if the rulebook for fighting infection has been partially erased. This state of lowered guard coincides with a reactivation of latent viruses. Studies consistently show that astronauts shed viruses like Epstein-Barr, cytomegalovirus, and herpes zoster, the virus that causes shingles, in their saliva and other bodily fluids at much higher rates in space. Their immune systems are no longer fully suppressing these lifelong stowaways. It is a silent rebellion from within, a body turning against its own protective protocols. But the environment adds a third, cruel layer to this storm. The microbes we bring with us to space are not passive either. Bacteria like Salmonella and Pseudomonas have been shown to become more virulent, more capable of causing illness under microgravity conditions. They form thicker, more resistant biofilms and can change their gene expression to better survive attack. So, picture the scenario: an astronaut with a dampened immune system, now hosting reactivated viruses, is living in a closed can where common bacteria have become unexpectedly potent. A simple cold or a minor infection, manageable on Earth, could spiral into a serious medical crisis millions of miles from the nearest hospital. This biological perfect storm means that the greatest threat to a mission's success might not be a meteor strike or a systems failure, but a mundane sore throat that the body simply cannot fight. A medical emergency on Earth triggers a cascade of response: an ambulance, a hospital, a team of specialists. In deep space, that cascade collapses into a terrifying stillness. The nearest emergency room is not minutes away, but over 6 months of travel, an impossible distance across a sea of nothing. This transforms a routine health issue into a potential mission-ending catastrophe. Every crew includes a medical officer, but this person is not a surgeon. They are an astronaut with additional medical training, equipped to handle minor injuries, distribute medication, and stabilize a patient using detailed protocols relayed from Earth. Their toolkit and knowledge are profound compromises designed for likelihood, not for every grim possibility. The true nightmare begins when a condition demands surgery. Performing an operation in microgravity is a challenge of almost surreal complexity. Blood does not pool in a wound. It forms floating, shimmering spheres that can obscure the surgical field and coat instruments. Organs no longer anchored by gravity drift from their familiar positions. A surgeon must physically tether themselves, their patient, and every single tool to prevent a chaotic drift of scalpels and sponges. Even a simple procedure like placing an intravenous drip becomes a high-stakes puzzle, as fluids form globules instead of flowing smoothly through tubing. Imagine the most critical act of earthly medicine: cardiopulmonary resuscitation. On the ground, you use your body weight to compress the chest. In zero gravity, you would simply push yourself away from the patient with equal force. Effective CPR would require both individuals to be strapped to a rigid backboard, a piece of equipment that may not even be on board. Now consider the conditions themselves. Appendicitis, a common and routinely treatable illness, would require an appendectomy in space, a complex abdominal surgery with immense risk of infection. A severe kidney stone, a perforated ulcer, or trauma from an accident during a spacewalk, any of these could lead to internal bleeding or sepsis. there are no blood banks for transfusions. No imaging machines beyond a basic ultrasound for diagnostics. No isolation ward for containing a rampant infection. The medical kit, however advanced, is a lifeboat, not a hospital. The harsh reality is that for certain serious conditions, the only viable treatment is an immediate return to Earth, an option that simply does not exist when you are orbiting Mars. This forces mission planners and crews into an unthinkable calculus. They must accept that some medical events, however tragic, may have only one outcome. It is the ultimate hidden danger, the acknowledgement that the human body, for all its resilience, remains fragile, and that the vastness which makes exploration glorious also makes it mercilessly lonely in a moment of crisis. The eyes are our most direct window to the universe, yet they are uniquely vulnerable to its invisible fury. Beyond the temporary swelling caused by fluid shifts lies a more permanent and insidious threat, one that steals clarity slowly and often silently. Space radiation carries a specific long-term danger for astronauts, a dramatically increased risk of developing cataracts at a young age. A cataract is a clouding of the eye's natural lens, the clear structure that focuses light onto the retina. On Earth, this is typically a condition associated with advanced age, a gradual hardening and yellowing of the lens proteins over decades. In space, the process is violently accelerated. The charged particles of galactic cosmic rays do not simply pass through the lens, they collide with its delicate cellular structure. Each high-energy particle acts like a microscopic bullet, shattering molecules and creating free radicals that damage the transparent cells. Unlike other tissues, the cells of the eye's lens are never replaced. They are simply packed tighter over a lifetime. Any damage incurred is permanent, accumulating like scratches on a priceless camera lens that can never be cleaned or swapped out. The effect is not immediate blindness, but a progressive fogging of vision that begins at the edges and creeps inward. Studies of astronaut medical records reveal a clear and sobering trend. Those who have spent longer periods in space, particularly on missions outside the relative protection of Earth's magnetic field like the Apollo lunar voyages, show a significantly higher incidence of early-onset cataracts. The risk appears to be dose-dependent, meaning every hour of exposure adds to the cumulative injury. This transforms space radiation from an abstract statistical risk into a very personal debt, one that may not come due until years after an astronaut has returned home and hung up their flight suit. They traded the sharp, brilliant vista of Earth from orbit for a future where their own world might gradually fade into a permanent haze. It is a delayed cost of exploration, a quiet reminder that some of the universe's prices are not paid at the moment of discovery, but in the long twilight that follows. Fire on Earth obeys predictable rules, rising upward in a familiar plume as hot air expands. In the microgravity of a spacecraft, those rules are rewritten entirely. Here, fire does not rise, it has no up. Instead, it becomes a slow, creeping sphere of chemical reaction, a ghostly blue orb that consumes oxygen and fuel in all directions at once. Without gravity to pull cooler, denser air away, the flame is starved of convection, becoming a languid, almost beautiful, and utterly deadly ball of heat that can drift along air currents to find new fuel. This changes everything about detection and suppression. On Earth, smoke alarms are placed on ceilings. In space, smoke can pool anywhere, and a smoldering electrical wire might hide its heat and toxic fumes behind a panel for hours before being discovered. The environment itself can be primed for disaster. To reduce the pressure differential on spacecraft hulls and to make spacewalks easier, some cabin atmospheres use a higher percentage of oxygen than we have on Earth. This is like turning the entire volume of the ship into a bellows. Materials that would only char on the ground, like fabrics or wire insulation, can become explosively flammable. A single spark from a short circuit, a malfunctioning device, or even static electricity can ignite a blaze that spreads with frightening speed. The true horror, however, lies in the absolute confinement. On a ship or a station, there is no fire escape, no jumping out a window. The crew is trapped with the growing inferno, breathing air rapidly filling with superheated toxins and choking smoke. Suppression methods are brutally limited. Water in droplets would float everywhere, potentially shorting other systems. Carbon dioxide extinguishers could suffocate the crew if used in a small module. The only recourse is often to seal off the affected section, a devastating choice if it contains critical supplies or, unthinkably, a crew member. History gave us a grim warning with the Apollo 1 tragedy during a ground test, where a pure oxygen atmosphere and an electrical fault led to a rapid, catastrophic fire. In the void of space, such an event would not just be a tragedy, it would be a tomb, a silent, burning end to a mission with absolutely nowhere to run. The materials we trust to protect us in the void are engaged in a silent, losing battle. Space is not a passive backdrop, but an active and corrosive environment that attacks the very substance of our ships and stations with tools we cannot see. One of the most insidious agents is atomic oxygen. In the upper reaches of Earth's orbit, intense ultraviolet radiation from the sun splits ordinary oxygen molecules into highly reactive single atoms. These atoms are ravenous to bond with anything they touch. For many spacecraft materials, especially polymers and composites, this is a death by a million tiny bites. The atomic oxygen slowly etches away surfaces, thinning protective coatings, degrading thermal blankets, and eroding the structural integrity of critical components over time. It is a form of rust, but one that works in a perfect vacuum. Alongside this, the unshielded ultraviolet radiation itself bombards plastics and adhesives, breaking the long-chain molecules that give them strength and flexibility. This ultraviolet embrittlement turns once supple seals and cable insulation into brittle, cracked hazards prone to sudden failure. The spacecraft is also subjected to a brutal thermal rhythm. Every 90 minutes in low Earth orbit, a vehicle swings from the blistering, direct sunlight, where temperatures can soar above 250 degrees Fahrenheit, into the profound shadow of Earth, where they can plummet to minus 250 degrees. This thermal cycling happens over 16 times a day, year after year. Metals, polymers, and glass expand and contract with each swing, a relentless mechanical stress that induces microscopic cracks. These fatigue cracks grow with each cycle, like bending a paperclip back and forth until it snaps. Perhaps the most deceptive threat, however, comes from within the spacecraft itself. The process is called outgassing. In the vacuum of space, trace amounts of solvents, adhesives, and other chemicals trapped within materials slowly vaporize and escape. These vapors do not simply disappear, they drift through the spacecraft and then condense onto the coldest surfaces they can find. Often, these are critical optical systems like camera lenses, sensor windows, or solar panel cover glass. A thin, contaminating film steadily clouds these surfaces, reducing their efficiency and clarity. A star tracker, which navigates by recognizing constellations, could be slowly blinded by its own habitat's exhalations. The terrifying commonality in all these processes is their inevitability and their silence. You cannot hear atomic oxygen etching a handrail. You cannot see a polymer becoming brittle until it suddenly cracks under stress. A camera's view does not fog overnight, but over months, until one day a critical docking maneuver is compromised by a blurred image. This slow, grinding degradation means that a spacecraft is never quite the same as the day it launched. It is always aging, always weakening. The systems we rely on for life, navigation, and communication are in a constant, invisible retreat. A mission to Mars would have no opportunity for replacement parts or servicing for years, trusting that materials tested for months in orbit will survive for a decade in the deeper space environment. It means every mission is, in a very real sense, a race against the quiet, unstoppable decay of its own bones. This silent decay of our machines points to a deeper philosophical danger, one that transcends engineering. As we reach out to touch other worlds, we carry with us an invisible, living cloud. Every spacecraft, every rover, every astronaut suit is a biological ark, teeming with millions of microscopic Earth stowaways. These microbes, resilient bacteria and hardy fungi, can survive in the extreme conditions of launch and the vacuum of space, lying dormant on surfaces. When we land on Mars or Europa or any other celestial body with the potential for past or present life, we risk unleashing them. This is the peril of forward contamination. Imagine our most profound scientific quest, the search for extraterrestrial life, being compromised before it even begins. A robotic arm scoops up a soil sample, and inside the most sensitive laboratory ever built, we detect organic molecules. The celebration would be global, but then a haunting question arises. Are we seeing the chemistry of Mars, or did we bring the chemistry with us? Is that bacterium we found truly alien, or is it a common Earth microbe from Florida that simply endured the journey? Distinguishing between the two could be scientifically nightmarish, potentially rendering billions of dollars and decades of work inconclusive. We could forever muddy the waters of another world with our own biological noise. To prevent this, space agencies adhere to strict planetary protection protocols. Probes destined for sensitive areas, like the Martian polar regions or the subsurface ocean of Europa, are assembled in clean rooms and subjected to intense heat or chemical sterilization. But absolute sterility is a myth. Microbes are tenacious, hiding in the tiniest crevice of a circuit board or within a sealed component. We can reduce their numbers dramatically, but we cannot promise zero. The more ambitious our missions become, with human explorers who cannot be baked in an oven, the more impossible this guarantee becomes. This leads to the mirror image fear, back contamination. It is the staple of science fiction, the notion of an astronaut returning with a strange space plague. While the likelihood of an extraterrestrial organism being able to infect terrestrial life is considered extremely low, the potential consequence is so vast that it cannot be ignored. The protocols for a crew returning from Mars would be unprecedented. They would likely enter a period of strict quarantine, not for days but for months, in a high-security facility while every sample and piece of equipment is scrutinized. The goal is to act as a biological firewall, protecting Earth's biosphere from an unknown it did not evolve to face. These twin dangers force us to confront a humbling responsibility. We are no longer just explorers, we are gardeners, or perhaps caretakers, of a cosmic ecosystem we are only beginning to understand. A single careless act could erase the unique story of another world, or inadvertently write a tragic new chapter for our own. Our sun is not a placid ball of light, but a churning sphere of nuclear fury with a violent temper. While galactic cosmic rays are a constant drizzle, solar storms are the hurricanes, sudden and ferocious outbursts that can transform a quiet journey into a fight for survival. These events come in two devastating forms. A solar flare is a brilliant flash of X-rays and extreme ultraviolet radiation, a burst of light that reaches Earth in just over 8 minutes, bathing everything in its path. Far more dangerous for spacefarers is the coronal mass ejection, a CME. This is the sun belching out a colossal bubble of its own atmosphere, a billion-ton cloud of magnetized plasma packed with high-energy protons. Think of the difference between the flash of a camera and the physical punch of a tidal wave. The CME is the wave, traveling at millions of miles per hour, and when it arrives, it brings a storm of particle radiation so intense it can deliver a lethal dose to an unshielded astronaut in a matter of hours. The warning time is terrifyingly short. We might see the flare, the flash of light, giving us a few tens of minutes to brace, but predicting exactly when and where the slower, more massive CME will strike is an imperfect science. For a crew on a Mars transfer vehicle floating in the empty space between planets, the alert could mean they have less than a day to prepare for an impact that could last for days. There is no planet to hide behind, no global magnetic field to deflect the onslaught. The only defense is mass, sheer physical stuff to absorb the particles. This is why any credible interplanetary spacecraft must include a storm shelter, a small, heavily shielded compartment lined with water tanks, food supplies, or even the crew's own waste. In this cramped sanctuary, astronauts would wait out the storm, listening to the hail of protons drumming against the hull, knowing that the walls between them and oblivion are just thick enough. A mission without such a shelter is a gamble with cosmic odds, trusting that the sun's rage will not flare during the many months of transit. It makes the sun not just our source of light and life, but a capricious guardian that can, without warning, become the most immediate deadly force in the solar system. The sun's fury is a threat you can hide from, but there is no shelter from the simple, crushing reality of home. After months or years in the gentle deception of microgravity, the human body undergoes a profound unlearning. Bones, having shed their mineral density, become fragile and porous. Muscles, especially those of the legs and back, atrophy from disuse. The cardiovascular system grows accustomed to an effortless flow, forgetting how to fight gravity's constant pull. This is the hidden trap of return, the physiological danger of readapting to gravity. The moment an astronaut lands, whether in the ocean or on the steppe, Earth reasserts its command with a violence that can be crippling. The most immediate and visible risk is to the skeleton. Imagine a bone that has lost 20% of its density, similar to the early stages of a severe age-related condition. Now, ask that bone to suddenly support the full weight of the body, to absorb the impact of a simple step off a ladder. The risk of a fracture, particularly in the weight-bearing bones of the hips, spine, and legs, becomes shockingly high. An astronaut could walk on Mars only to break a femur back on Earth during a seemingly routine exit from the capsule. This is not mere weakness, it is a structural failure waiting for the first real load. Simultaneously, the body is struck by a wave of dizziness so severe it can cause immediate collapse. This is orthostatic intolerance. The heart, now too weak and lazy, cannot pump blood upward to the brain against the sudden, forgotten force of gravity. Blood pools in the legs and abdomen. The brain, starved of oxygen, sends a desperate signal and the world goes dark. Astronauts are routinely carried from their spacecraft not out of ceremony, but out of medical necessity. They simply cannot stand. The rehabilitation that follows is a long, painful process of rebuilding from the inside out. It is not like recovering from an athletic injury. It is like teaching the body its most basic functions all over again. Balance must be relearned. Bones must be coaxed to slowly regain their strength over many months, with no guarantee they will ever fully recover their pre-flight integrity. The cruel irony is profound. The greatest physical trial of an interplanetary mission may not be surviving the alien environment, but surviving the return to the familiar embrace of our own world. The body pays a debt for every day spent in the void, and the final, heaviest payment comes due upon landing. The human body's struggle with gravity is matched by another quiet war, one fought in the gut. On a multi-year mission to Mars, food is not just comfort, it is life support, medicine, and a pillar of psychological health. Yet the very nature of space travel undermines this foundation in hidden ways. The first challenge is time. Every morsel must be shelf-stable for years, enduring radiation and temperature swings. This processing and long-term storage inevitably degrades key nutrients. Vitamins, especially fragile ones like C and B vitamins, slowly break down. Antioxidants lose their potency. The colorful, nutrient-rich foods of Earth become pale, processed shadows of themselves. Over months, this can lead to subtle but dangerous deficiencies, weakening bones, impairing wound healing, and compromising the immune system at the very time it is under siege. But the danger goes deeper than the food itself, into how the body processes it. Microgravity confuses our digestive system. Without gravity to guide things along, food and gas can linger uncomfortably in the stomach and intestines. The entire process becomes less efficient, and nutrient absorption can be erratic. This physical discomfort is compounded by a more profound disruption, the gut microbiome. This vast ecosystem of bacteria inside us is now understood to be a master regulator, influencing not just digestion but immunity, inflammation, and even brain chemistry and mood. On Earth, we constantly replenish and diversify this internal garden through fresh, varied foods. In space, the limited, sterile, processed diet acts like a famine for these microbial communities. The diversity plummets, harmful bacteria can gain the upper hand. This imbalance, known as dysbiosis, is linked on Earth to higher risks of illness, low-grade inflammation, and challenges with mental well-being. For an astronaut, this means the closed loop of the spacecraft extends inward. A degraded diet may not only weaken the body's defenses, but also subtly erode resilience and cognitive sharpness through the gut-brain axis. The menu becomes a critical engineering and medical problem where the solution is not just calories, but cultivating an entire internal ecology millions of miles from the nearest farm. The spacecraft is never truly silent. Beneath the grand silence of the cosmos lies a constant mechanical symphony of survival. Fans whir to circulate air, pumps thrum to move fluids, and life support systems generate a pervasive, low-frequency vibration that resonates through the very bones of the ship. This is not the occasional sound of a busy office or a city street. It is an unrelenting, high-decibel environment that becomes the inescapable soundtrack to every moment of an astronaut's life. On the International Space Station, noise levels in some modules can consistently reach the volume of a busy restaurant or a vacuum cleaner, often exceeding 70 decibels. Imagine trying to sleep, to concentrate on a complex repair, or to simply find a moment of mental quiet with that relentless hum as your constant companion. The first and most direct casualty is hearing. Prolonged exposure to this level of noise inflicts cumulative, permanent damage on the delicate hair cells of the inner ear. Astronauts return from long-duration missions with measurable hearing loss, a hidden disability traded for time in orbit, yet the harm extends far beyond the ears. This chronic noise pollution is a potent physiological stressor. It triggers the body's fight or flight response, elevating heart rate and stress hormone levels like cortisol, even when the crew is consciously trying to ignore it. This constant low-grade alarm state wears down resilience, contributing to fatigue and irritability. Perhaps most critically, it sabotages the very rest needed to recover. Sleep in space is already challenged by the strange circadian rhythms of a sunrise every 90 minutes. Add a relentless acoustic assault, and deep, restorative sleep becomes nearly impossible. Crews report frequent awakenings and poor sleep quality, leaving them perpetually under-rested. This fatigue cascade impairs judgment, slows reaction time, and erodes the cognitive sharpness required for split-second decisions. Communication, the lifeline of any mission, also suffers. Vital conversations between crew members or with mission control millions of miles away can be garbled or misunderstood over the background roar, leading to dangerous errors. The noise is more than an annoyance. It is a slow, environmental poison that degrades human performance from every angle, turning the habitat from a safe haven into a chamber of inescapable sensory strain. Our machines hum with a silent intelligence we have come to trust absolutely. We design them to think, to adapt, to handle the thousands of tiny decisions we cannot make from light minutes away. This reliance on flawless software and autonomous systems is not a convenience, it is the bedrock of deep space travel. Yet within every line of code lies a ghost, the potential for a single, catastrophic misinterpretation. A software bug is not like a mechanical failure. You cannot see it wear down. It sleeps within millions of instructions, waiting for one specific, unlikely combination of inputs to wake it. Imagine a navigation system tasked with calculating a trajectory correction burn. A rounding error in its algorithm, a tiny mathematical drift accumulated over months, could plot a course that sends the spacecraft not toward a safe orbit, but on a path that grazes a moon's gravity well, slinging it irrevocably into the void. The crew might not know until it is far too late. The danger compounds with our increasing dependence on artificial intelligence as a co-pilot. An AI system monitoring life support is trained on millions of simulated scenarios, but space is a master of the unforeseen. A sensor fails, reporting that carbon dioxide levels are plummeting. The AI, interpreting this as a failure of the carbon scrubbers, might logically decide to shut them down to conserve power, not realizing the sensor itself is broken. In reality, carbon dioxide is rising silently, and the system just turned off the only thing keeping the air breathable. The human crew, trusting their automated guardian, might not detect the truth until headaches and confusion set in. The most chilling aspect is the lag. On a mission to Mars, a signal from Earth can take up to 22 minutes to arrive. A real-time conversation is impossible. If an autonomous system makes a wrong choice, the crew on board has only moments to recognize the error, understand its cause, and execute a manual override before the consequences become irreversible. They are fighting a cascade of automated logic with human instinct, separated from help by an impassable gulf of time and space. We ask these systems to be perfect in an imperfect universe, to navigate ambiguities they were never designed to understand. The hidden danger is not that the machines will rebel, but that they will obey their programming with a cold, flawless logic that leads, step by perfect step, to disaster. Every line of code depends on a single, non-negotiable resource: electrical power. In the isolation of space, a total blackout is not an inconvenience, it is a slow, certain end to everything. The spacecraft becomes a frozen, silent tomb drifting in absolute darkness. The threats to this vital flow are numerous and often silent. For missions within the inner solar system, we rely on the Sun, deploying vast wings of solar arrays to catch its light. Yet these delicate panels are supremely vulnerable. A single impact from a micrometeoroid or a piece of orbital debris can shatter a cell or slice through a critical power cable, crippling a panel's output. The damage might be gradual, a slow bleed of efficiency that goes unnoticed until reserves are dangerously low. On a world like Mars, a new enemy blankets the panels themselves: dust. The fine, pervasive regolith settles on every horizontal surface, and without rain or wind to clear it away, it steadily accumulates, turning the transparent surfaces into frosted glass. A dust storm could reduce power generation to a trickle for weeks, forcing the crew into a desperate power-saving mode with no guarantee the skies will clear in time. For missions venturing farther from the Sun, where sunlight is too weak, we turn to nuclear power in the form of radioisotope thermoelectric generators. These RTGS are remarkably reliable, creating power from the natural decay of plutonium, but they have no moving parts to repair, and their output slowly decays over decades. If one fails prematurely, there is no restarting it. Fuel cells, which combine hydrogen and oxygen to produce electricity and water, are another option, but they are consumable. Once their reactants are gone, the cell is dead. The true terror of a power failure is not the darkness, but the domino collapse it triggers. First, heating fails. The temperature plummets toward the deep cold of space, freezing any remaining water lines and making the habitat uninhabitable within hours. Next, the whirring fans and pumps of the life support system fall silent. Carbon dioxide begins to accumulate unscrubbed. Oxygen generation stops. The water recycler, a complex piece of machinery that purifies every drop of sweat and urine, shuts down, condemning the crew to thirst amidst a ship full of undrinkable fluid. Finally, and most isolating of all, communications die. The last lifeline to Earth, the voices of mission control, vanishes into static. The crew is utterly alone, sitting in the freezing dark, watching their air go bad. Power is the heartbeat of the mission, and when it stops, every other system follows in a swift, chilling succession. That lifeline of power also carries our most precious cargo, our connection to home. The constant chatter of mission control, the stream of data, the reassuring voices of loved ones, all travel as faint whispers on beams of light or radio waves across the immense gulf. To lose that connection is to be severed not just from help but from humanity itself. This communication blackout is a psychological and operational void that opens up without warning. The causes are varied and often mundane. A powerful solar flare can ionize Earth's upper atmosphere, creating radiostatic that drowns out signals for hours. A critical amplifier on the spacecraft could simply overheat and fail. A misaligned antenna, jarred by a micrometeoroid impact or a clumsy maneuver, might point its beam into empty space, talking to stars that do not talk back. On the surface of another world, the terrain itself can be the enemy. A mountain range or a deep crater wall rising up to block the line of sight to the orbiting relay satellite. For a crew on Mars, there are scheduled blackouts every night when their base rotates away from Earth, a predictable silence, but an unscheduled, prolonged silence is a different kind of terror. Operationally, it is paralyzing. A complex repair procedure, a puzzling medical symptom, a navigation anomaly. All of these challenges are met with a vast, echoing quiet where guidance should be. The crew is thrown entirely on their own collective knowledge and the limited library of procedures stored on board. They become their own mission control, with no one to double-check their math or suggest an alternative they had not considered. The weight of every decision multiplies exponentially, with no safety net of expertise from thousands of engineers on the ground. But the deeper cut is psychological. The voices from Earth are more than instructions. They are a tether to normalcy, to shared experience, to the rhythm of a world that continues to turn. Their loss creates a profound and chilling isolation. The spacecraft or habitat, once a vessel of exploration, transforms into the smallest, loneliest island in an infinite, silent sea. Every beep and hum of the ship becomes magnified in the absence of outside voices. Time stretches, doubts grow. The mind can begin to question reality itself, wondering if the silence means something has gone catastrophically wrong back home, or if they have simply been forgotten. This absolute solitude is a hidden stressor more potent than any radiation, because it attacks the fundamental human need for community and confirmation. To work a problem in that silence, knowing a mistake could be fatal and that no one is coming to help, is to stare into the true abyss of deep space travel. Our reliance on flawless machines assumes they are bathed in a predictable environment, but space removes the most fundamental force we take for granted. Gravity is the quiet choreographer of our world, directing the flow of everything from a cooling breeze to the blood in our veins. Remove it, and the most basic processes rebel in strange and dangerous ways. This is the hidden danger of altered fluid dynamics, where the rules of flow, mixing, and heat transfer are rewritten. Without gravity, convection simply stops. On Earth, hot air rises because it is less dense than the cooler air around it, creating a natural circulation that carries heat away. In microgravity, hot air does not rise. It simply sits, forming a stagnant, overheated bubble around whatever generated it. For a spacecraft's electronics, this is a critical problem. A computer chip or a power converter that would cool itself through natural air movement on Earth now stews in its own waste heat. Unless fans are constantly and perfectly circulating the air, these hotspots can lead to unexpected failures as components quietly cook themselves to death. The same principle threatens the astronauts themselves. During intense physical exertion, the human body relies on convection and sweat evaporation to shed excess heat. In the still air of a spacesuit or a station module, that heat cannot dissipate efficiently. Sweat does not drip away, it forms sticky beads on the skin, and the hot, humid air clings to the body. An astronaut performing a strenuous spacewalk could overheat dangerously, their core temperature rising with no natural environment to carry the warmth away. The unpredictability extends to the ship's vital fluids. Managing fuel for engines and thrusters becomes a high-stakes puzzle. In a tank, liquid propellant does not settle at the bottom. It forms a free-floating blob, sloshing in any direction. To feed an engine, spacecraft use complex systems of baffles, sponge-like metal structures, or even small thrusters to push the fuel toward the intake. If this fails, the engine experiences fuel starvation, gulping vapor instead of liquid and potentially causing a catastrophic shutdown or explosion mid-maneuver. Even something as simple as drinking water illustrates the peril. Bubbles of air which would float to the top in a glass on Earth remain suspended throughout the liquid in space. An astronaut taking a sip from a pouch could ingest a large bubble of air, leading to unexpected discomfort or even interfering with nutrient absorption. From the microscopic scale of cellular fluid balance to the macroscopic scale of rocket propulsion, the universe without its anchor force is a place where nothing flows as expected, where every pump, every fan, and every beating heart must contend with a physics that feels profoundly and sometimes perilously wrong. The closed ecosystem of a spacecraft does more than just stress the human body. It actively reshapes the microscopic world we carry with us. Within the sealed metal walls, a quiet but relentless experiment in evolution is underway. The bacteria and fungi that naturally live on our skin and in our bodies, along with those that hitch a ride on equipment and supplies, find themselves in an unprecedented environment. They are bathed in higher levels of radiation, subjected to microgravity, and exposed to the constant chemical traces of cleaning agents and antibiotics used to maintain a sterile environment. This is not a static habitat, it is a high-pressure training ground. Under these stresses, microbes do what they have done for billions of years: they adapt. Research has shown that certain bacteria, including strains that can cause illness, undergo changes in microgravity. They often form thicker, more complex communities called biofilms. Picture a slimy, protective fortress that clings to surfaces inside water lines, on air filters, or even on medical equipment. This biofilm shield makes them incredibly difficult to kill, protecting the bacteria inside from antibiotics and standard disinfectants. Even more concerning, studies indicate some bacteria can increase their virulence, their ability to cause disease, and can develop resistance to multiple antibiotics more quickly in this unique setting. The spacecraft, in essence, becomes an accidental laboratory for cultivating a potential superbug. Now layer this over the earlier danger of the astronauts' weakened immune systems. The crew's natural defenses are already in a diminished state, less vigilant and less effective. If a resilient, adapted pathogen were to break loose within the habitat, perhaps from a contaminated water line or a minor wound that becomes infected, the consequences could be dire. A simple infection that would be a minor nuisance on Earth could escalate into a systemic crisis that available medicines cannot touch. The medical kit, with its limited range of antibiotics, might be useless against a microbe that has evolved new defenses in the depths of space. This transforms the habitat from a safe haven into a paradox, a place where our most stringent efforts to control the microbial environment might inadvertently be training the very enemy we fear. The crew is not just living with their own microbiome, they are living with an evolving one, a hidden passenger on the voyage that is learning, generation by generation, how to survive them. The view of Earth from orbit is not just a sight, it is a profound psychological anchor. For astronauts circling our planet, the steady rotation of that vibrant blue marble provides a constant, comforting reminder of home, of life, of everything they know and love. It is a visual tether that has supported human minds in the void for decades, but on a voyage to Mars that tether is cut. This is the Earth out of view phenomenon, and its psychological impact is a hidden danger far deeper than simple homesickness. Over weeks and months, Earth shrinks in the window from a world to a point of light, and then, eventually, it vanishes entirely into the sun's glare. The daily reassurance of its presence is gone, replaced by an unbroken panorama of blackness and distant, uncaring stars. In this new reality, a profound existential loneliness can take root. The astronaut is no longer orbiting home, they are truly leaving it behind. All of human history, every forest, every ocean, every city, and every face is now contained on a pale dot that has disappeared from sight. The mind can grapple with this intellectually, but emotionally it is a staggering weight. The comforting cycles of day and night, of weather patterns and familiar continents sliding past, are replaced by a static, infinite depth. This loss can trigger a form of cosmic melancholy, a feeling of being not just physically distant, but existentially adrift. Research from analog missions and polar expeditions suggests that without the visual anchor of a living world, individuals can experience a flattening of emotion, a decline in motivation, and a deep sense of isolation that mere communication cannot cure. Hearing a voice from Earth is one thing, but not being able to see the world that voice comes from creates a cognitive dissonance that can erode one's sense of place in the universe. The danger is not a sudden breakdown, but a gradual, quiet diminishing of the spirit, where the majesty of the cosmos becomes a mirror reflecting only one's own profound smallness. The mission continues, the work goes on, but the internal compass that once pointed unequivocally toward home now spins freely in the dark. This disconnection challenges the very human need for a horizon, for a place to belong, raising a haunting question for our future explorers. Can we remain fully ourselves when we can no longer see the world that made us? The air inside a spacecraft is a carefully crafted illusion of Earth, a fragile bubble of breathable gas that must be maintained with absolute precision. Every exhale, every off-gassing panel, every operation of machinery adds a trace of something alien to that mix. This is the silent, invisible hazard of toxic atmosphere buildup, where the very systems designed to keep us alive can turn against us if a single component falters. The primary task is managing the obvious carbon dioxide. Each crew member exhales about 2 pounds of it every day. Without removal, it would accumulate rapidly, leading to headaches, confusion, and eventually loss of consciousness. The scrubbers that filter it out are engineering marvels, but they are just one part of a much more complex chemical battlefield. The human body itself is a factory of trace contaminants. We exhale acetone and methanol. Our skin releases ammonia and other organic compounds. The materials around us constantly exhale as well, a process called off-gassing. Plastics, adhesives, and insulation slowly release volatile organic compounds, or VOCs, like formaldehyde or benzene into the enclosed air. Even equipment like experiments or electronics can have small, undetectable leaks of coolants or solvents. On Earth, these trace gases are harmless, diluted to nothing by our vast, turbulent atmosphere. Inside a sealed metal can millions of miles from home, there is nowhere for them to go. They simply accumulate part per million by part per million, day after day. The life support system must therefore act as both a lung and a liver, not just swapping oxygen for carbon dioxide, but actively scrubbing dozens of other chemical threats from the air. Activated charcoal filters, catalytic burners, and specialized chemical beds work in concert to trap or break down these contaminants. The danger lies in a single point of failure. Imagine a charcoal filter that has reached its absorption limit a month earlier than predicted. or a catalytic reactor whose delicate catalyst is poisoned by an unexpected chemical from a new piece of equipment. The failure might not trigger an alarm immediately. Instead, it begins a slow, insidious process. A crew member might start experiencing persistent nausea or a dull headache attributed to space adaptation syndrome. Others might report a strange metallic taste or increasing fatigue. These are the vague, early symptoms of low-level poisoning from carbon monoxide or VOCs. By the time the cause is identified, the entire crew could be suffering from impaired judgment and slowed reflexes, precisely when they need to troubleshoot the failing system. There is an even more volatile risk. Some accumulated gases, like methane or hydrogen from a malfunctioning electrolysis unit, are not just toxic, they are explosive. Mixed with the cabin's oxygen in the right concentration, a single spark from a switch or a static discharge could ignite a flash fire of devastating force. This transforms the spacecraft atmosphere from a life-giving resource into a potential chemical weapon of our own making, demanding constant vigilance over an invisible, slowly shifting balance that we cannot afford to lose. The air we breathe is a delicate balance, but the very sense that tells us which way is up is thrown into chaos the moment we reach orbit. Our balance system, a masterpiece of evolution fine-tuned for Earth, relies on a constant conversation between the inner ear and the eyes. Tiny fluid-filled canals and calcium crystals in the vestibular system sense gravity's pull and head movement, while our vision confirms what we see. In microgravity, that conversation becomes a screaming argument. The inner ear's fluid floats freely, and its crystals drift, sending chaotic, false signals of constant tumbling or spinning to the brain. Meanwhile, the eyes report a stationary spacecraft interior. This sensory conflict is the root of a debilitating condition known as space motion sickness, and for most astronauts it is an unavoidable rite of passage. The symptoms are visceral and overwhelming: a sudden cold sweat, intense nausea, disorientation so severe it can be impossible to tell left from right, and often vomiting. This is not a minor travel discomfort. It is a full-scale neurological revolt that can render a highly trained individual utterly incapacitated for 1 to 3 days. The timing could not be more perilous. These first critical days in orbit are often packed with dynamic, precision tasks like docking with a space station, conducting initial system checks, or performing urgent spacewalks to inspect the vehicle after launch. An astronaut struggling with vertigo and the urgent need to be sick inside their helmet is in no condition to manipulate delicate controls or make split-second decisions. A misaligned docking, a misread gauge, or a delayed reaction could cascade into a catastrophic failure during the mission's most vulnerable phase. Even after the acute sickness passes, the disorientation lingers. Reaching for a floating tool becomes a conscious calculation, not an instinct. The brain must painfully rewire itself to trust its eyes over its inner ear, a process that takes time and constant mental effort. For a crew on a short mission, this lost productivity is a serious setback. On a years-long voyage to Mars, it represents a dangerous period where the crew's collective capability is significantly degraded right at the start. The body's rebellion against the new reality of weightlessness is a stark reminder that our most fundamental senses, the ones we never think about, can become our first and most immediate adversaries in the final frontier. The human blueprint itself may not survive the journey unchanged. Beyond the immediate damage from radiation lies a deeper, more subtle threat, one that operates at the very code of our existence. Emerging research points to a dual assault on our genetics in space, involving both direct harm to our DNA and profound changes in how our genes are expressed. The first part is straightforward in concept, if terrifying in scale. The relentless hail of high-energy particles does not just pass through tissue, it can slice through the double helix of DNA like molecular scissors. Our cells have remarkable repair mechanisms, but in the bombardment of deep space, these systems can become overwhelmed. Unrepaired or misrepaired breaks can lead to mutations, errors in the genetic instructions that, if they occur in certain genes, can initiate the development of serious illness years down the line. This is the well-established long-term cancer risk, but scientists are now uncovering something even more complex and less understood: epigenetic changes. Epigenetics is like the software that runs on the hardware of our DNA. It involves chemical tags and markers that attach to our genes, telling them when to turn on, turn off, or dial their activity up and down. These markers are influenced by environment, diet, and stress. The extreme environment of space, it appears, can rewrite this software. Studies of astronauts and animal models returning from space show significant alterations in these epigenetic markers, affecting genes related to immune function, bone metabolism, and neurological processes. The body, in essence, is reprogramming itself in response to an alien world. The immediate concern is what this reprogramming means for an astronaut's lifelong health. Could these epigenetic shifts accelerate aging-related processes or create vulnerabilities we do not yet comprehend? But there is a more profound and ethically staggering question that follows. Some epigenetic changes can be passed from parent to child. If an astronaut's gene expression is fundamentally altered by years on Mars, could those changes and the potential health risks they carry be inherited by their children? This moves the danger from a personal, accepted risk to a generational one. It forces us to confront a new frontier in ethics. Does humanity have the right to embark on journeys that might rewrite the biological inheritance of future generations? The research is still in its infancy, and the full implications are a shadow on the horizon of our ambition. Yet it suggests that the price of planting flags on distant worlds may be written not just in the bones and blood of the explorers, but in the silent language of their genes, a legacy passed forward into a future we are only beginning to imagine. Every breath and every sip of water on a long-duration mission is a borrowed resource, reclaimed from what the body discards. The life support system is a mechanical miracle, a closed-loop ecology that must mimic the vast, self-cleaning processes of Earth within the cramped confines of a spacecraft. It is also a terrifyingly fragile single point of failure. The reality is stark. The water you drink on a journey to Mars will have been, quite recently, the sweat on your skin and the moisture in your breath, meticulously filtered and purified. The same air you exhale, laden with carbon dioxide, must be scrubbed clean and replenished with fresh oxygen, often extracted from that same recycled water. This elegant loop is a house of cards. Consider the water processor, a complex assembly of filters, chemical beds, and distillation units. It must handle not just urine, but humidity from the air and wastewater from hygiene. A key component, like a pump that circulates the fluid through a purification membrane, could fail, or a sensor monitoring contaminant levels might malfunction, allowing a buildup of ammonia or other toxins to slip through. The crew would not know until they began experiencing the vague symptoms of low-grade poisoning, or until the system clogs and halts entirely. Suddenly, the reassuring trickle of fresh water stops. There are no rivers to tap, no clouds to gather. Every drop already aboard is now a finite and dwindling treasure. The same grim logic applies to the air. The carbon dioxide scrubbers are the lungs of the ship, typically using beds of a material like zeolite to absorb the gas. When one bed is saturated, it is heated to release the carbon dioxide into space, and the cycle continues. If the heating mechanism fails, that bed becomes permanently saturated, useless. The remaining scrubbers must work overtime, and if they too fail, the carbon dioxide concentration begins a slow, inexorable climb. Headaches and lethargy are the first warnings, followed by impaired judgment, and finally, unconsciousness and the end. The true horror of this closed loop is the absence of a backup plan in the traditional sense. You cannot carry 2 years of spare air and water for a crew of 4. The mass would be impossible. the recycling system is the only thing standing between the crew and a swift, silent conclusion. Its failure means the habitat transforms from a vessel of life into a sealed container where the very byproducts of existence become the agents of its end. This transforms waste management from a sanitary concern into the most intimate and critical engineering challenge of all, asking us to place our ultimate trust in a machine that must never, ever stop turning our refuse back into life. The ship's life support hums with a fragile certainty, but its survival depends on a world it left behind. Every deep space mission is tethered to Earth by an umbilical cord of funding, political will, and global stability. This may be the most unpredictable danger of all, a threat born not in the void, but in the halls of power and the fluctuations of economies back home. A voyage to Mars is a decade-long endeavor spanning multiple election cycles, international agreements, and budget appropriations. The crew launching on such a journey places their ultimate faith not just in engineering, but in the enduring commitment of the planet they are leaving. Imagine a scenario where halfway through the mission, a major geopolitical conflict erupts. The nations cooperating on the mission are now on opposing sides. The deep space network of antennas, vital for communication and navigation, could become a contested asset or be repurposed for military use. The steady stream of supply missions carrying food, spare parts, and fuel for the return journey might be indefinitely postponed, caught in the gridlock of international sanctions, or simply deemed a non-essential expenditure during a time of crisis. The crew orbiting Mars or living on its surface would continue to receive data, but the context of that data would shift. Updates from mission control might grow sparse, filled with gaps, or suddenly stop as priorities on Earth violently realign. They would be physicists and engineers, but they would also become unwilling students of distant political science, trying to decipher the silence from their home planet. An even more chilling possibility is economic collapse. Space exploration is phenomenally expensive, often justified as an investment in future technology and national prestige. During a severe global recession or depression, such programs are among the first to face drastic cuts. The public and political appetite for funding a distant adventure evaporates when immediate needs on Earth become overwhelming. A mission could find its funding slashed mid-flight, forcing a frantic, bare-bones effort just to keep the crew alive with no resources allocated for the complex maneuvers required to bring them home. The stranded crew would become a symbol of a forgotten ambition, a ghost ship from a more optimistic time, awaiting a rescue that the people of Earth may no longer have the will or the means to mount. This transforms the mission from a technical endeavor into a profound act of trust. The astronauts are betting their lives that the world they left will remain, in its essential character, the same world willing to welcome them back. It is a reminder that the courage to leave Earth must be matched by an equal measure of steadfastness from those who stay behind, a stability we can never fully guarantee. The promise of a self-sustaining ship includes the ability to build what it needs along the way. 3D printers and fabrication labs are heralded as the solution to the spare parts problem, allowing crews to manufacture tools, components, and even medical devices from raw materials or recycled plastic. Yet this vision of in-space self-reliance carries its own set of hidden perils, transforming the machine meant to save us into a potential single point of catastrophic failure. The first danger is in the very substance of what it creates. On Earth, gravity provides a constant, uniform force during the printing process, helping layers of molten plastic or metal settle and bond in predictable ways. In microgravity, that force vanishes. The material does not settle, it floats. This can lead to weak layer adhesion, microscopic bubbles trapped within the structure, and warping as the material cools without gravity to hold its shape. A bracket printed in space might look identical to one made on Earth, but its internal crystalline structure could be flawed, making it brittle and prone to sudden fracture under load. A crew member relying on that bracket to hold a critical life support component in place would have no way of knowing it is a silent time bomb until the moment it shatters. The fabrication unit itself is a complex machine filled with moving parts, heaters, and precision nozzles. It is subject to the same wear and tear, vibration, and radiation as every other system on board. If the printer breaks, the crew loses their factory. Repairing a high-precision 3D printer requires specialized tools and knowledge, and possibly parts that can only be made by another printer, creating a paralyzing paradox. This shifts the risk from not having a specific spare part to relying entirely on a machine that must remain perpetually operational in an environment hostile to precision. The peril escalates dramatically when the needed repair is not inside the cabin, but on the ship's external skin. An emergency spacewalk to fix a micrometeoroid puncture or a damaged radiator is arguably the most dangerous single activity in human spaceflight. An astronaut, encased in a bulky suit with limited dexterity and visibility, must navigate to the damage site, often using cumbersome tethers and tools not designed for the specific, jagged tier they encounter. Their gloves are thick, their fingers numb. Every movement is a fight against pressurized suit joints. The repair itself, perhaps applying a sealant patch or replacing a panel, becomes a ballet of immense complexity under the relentless glare of the sun and the deep freeze of shadow. A single mistake, a snagged tether, a tool drifting away, or a tiny puncture in the glove could turn a repair mission into a lethal crisis. The terrifying reality is that some external damage, especially to the heat shield of a vehicle destined for atmospheric entry, may be utterly irreparable with the tools and time available. In space, manufacturing offers a compelling dream of independence, but it demands we trust the untested integrity of its products and the flawless execution of its most desperate procedures, where every printed layer and every gloved maneuver carries the weight of survival. Our biological clock is tuned to a rhythm that does not exist beyond Earth. On the International Space Station, the sun rises and sets 16 times a single day. This relentless 90-minute cycle of light and dark is a form of sensory bombardment that the human body was never designed to endure. Our circadian rhythm, that internal metronome governing sleep, hormone release, and cellular repair, depends on consistent environmental cues, primarily the steady 24-hour march of daylight into darkness. In orbit, that anchor is cut loose. The body's master clock, located deep within the brain, receives chaotic signals. Is it time to wake or time to sleep? The confused system begins to drift, and with that drift comes a cascade of hidden dysfunctions that erode an astronaut from the inside out. The most immediate casualty is sleep itself. Despite strict schedules, crews consistently report poor sleep quality, frequent awakenings, and a feeling of never being fully rested. This is not simple insomnia. It is a fundamental disconnect between the body's need for rhythm and the environment's chaotic offering. The consequences of this chronic misalignment are profound and far-reaching. Metabolic processes go awry. The carefully timed release of hormones like cortisol, which helps manage stress, and melatonin, which signals sleep, becomes erratic. This can lead to shifts in appetite, unexpected weight loss or gain, and a disruption in how the body processes sugars and fats, subtly increasing the risk of metabolic illness over time. Perhaps most dangerously, cognitive function suffers. The fog of sleep deprivation clouds judgment, slows reaction time, and impairs the complex, split-second decision-making required in an environment where errors are unforgiving. This mental fatigue compounds the psychological strains of isolation, creating a vicious cycle where stress further disrupts sleep, and poor sleep amplifies stress. The assault does not stop at the brain. A robust circadian rhythm is a conductor for the immune system, orchestrating the activity of defender cells to peak at certain times. When the rhythm is shattered, this coordination breaks down. Immune cells become less vigilant and less effective, leaving the body more vulnerable to the reactivated viruses and adapted bacteria lurking within the habitat. On a future Mars mission, the problem inverts but persists. A Martian day, called a sol, is about 39 minutes longer than an Earth day. This seemingly minor difference is enough to throw the human circadian cycle permanently out of sync. The body will constantly try and fail to adjust by those 39 minutes each day, leading to a permanent state of low-grade jet lag that could last for years. The hidden cost is a crew operating in a perpetual twilight of fatigue, their biological foundations subtly undermined, making every other danger, from radiation to psychological stress, that much harder to bear. The greatest danger may not be a failure of the ship, but a failure of the collective mind within it. High-stakes isolation creates a pressure cooker for human judgment, where the very dynamics meant to ensure survival can begin to work against it. This is the hidden peril of groupthink and decision-making under extreme stress. In the confined, high-consequence world of a spacecraft, descent is not just uncomfortable, it can feel dangerous. A crew becomes a family, but also a unit where harmony is prized, and rocking the boat could mean jeopardizing critical teamwork. In this environment, a junior member might hesitate to question a senior officer's flawed assumption. A technician, noticing an anomaly that contradicts the group's agreed-upon diagnosis, might dismiss their own observation, believing everyone else must be right. The desire for consensus and cohesion silently overrides the rigorous, skeptical analysis that complex systems demand. Poor decisions are not corrected, they are reinforced through mutual, unspoken agreement. The crew, already battling the disorienting effects of circadian disruption and chronic fatigue, now faces a crisis. Perhaps a primary life support indicator is flashing red, but a backup sensor shows green. The initial group assessment, formed under time pressure, leans toward a sensor failure. But what if the backup sensor is wrong and the life support system is genuinely failing? As minutes tick by, the stress compounds, fatigue narrows focus, tunneling vision onto a single, possibly incorrect solution. The ability to mentally step back, to generate and coldly evaluate alternative scenarios evaporates. Communication becomes terse, aimed at executing the plan rather than re-examining it. The dissenting voice, if it exists, is now seen not as a valuable check, but as an obstacle to decisive action. In the terrifying quiet after a mistake is made, the realization dawns that the error was not in the machinery, but in the conversation about it. The crew's greatest strength, their interdependence, becomes a vulnerability when the need for unanimous resolve overpowers the duty to doubt. It is a subtle unraveling of reason where the right answer can be floating in the room, visible to someone, yet made invisible by the sheer weight of shared stress and the unspoken rule not to break the circle of trust. This final hidden danger has no sensor to detect it and no procedure to follow. We have catalogued radiation, isolation, mechanical decay, and biological rebellion, but the most profound peril on a journey to another world is the one we have not yet named. It is the phenomenon we have not anticipated, the flaw in our logic we cannot see, the cosmic interaction that lies just beyond the edge of our current understanding. History is a testament to this. When explorers first sailed across vast oceans, their greatest threats were not the storms they expected, but the scurvy they did not understand, the uncharted reefs that appeared from nowhere, and the cultural encounters for which they had no framework. They prepared for known monsters on their maps, only to be undone by the blank spaces. A voyage to Mars is our generation's equivalent of sailing off the edge of the map. We have models and simulations, but they are built from the physics and biology we know here, now, on Earth. What subtle, long-term effect might the combined radiation and microgravity environment have on complex pharmaceuticals, causing a vital medication to degrade or become toxic after 18 months? Could a unique resonance between the spacecraft's vibration and the fluid in a fuel tank, only achievable in the deep quiet between planets, cause a catastrophic structural fatigue no ground test could ever replicate. Perhaps it is something from outside our ship entirely, an unobserved property of the Martian dust that makes it explosively reactive under specific conditions inside a habitat airlock, or a previously undetected type of solar particle that bypasses our shielding entirely. The terrifying beauty of exploration is that it always reveals the limits of our imagination. We solve the 30 problems we can foresee, engineering marvels of resilience and redundancy. Yet the universe is a master of the unforeseen twist, the one in a billion combination of failures, the silent variable waiting in the dark. This is not a counsel of despair, but the ultimate argument for humility and relentless curiosity. The greatest hidden danger reminds us that courage is not the absence of fear, but the decision to venture forward knowing that the final, defining test may be one for which we can never fully prepare. It ensures that when we finally send humans to walk on that red soil, the greatest discovery might not be what we find there, but what we learn about our own capacity to face the absolute unknown. The 30 hidden dangers form a sobering mosaic, revealing space not as an empty highway but as an active and demanding environment. It is a place that challenges our biology, our psychology, our machines, and our very social fabric in ways we are only beginning to map. This long catalogue is not an argument against going, however. It is the opposite. To look clearly at these perils, from cosmic radiation to the quiet unraveling of group dynamics, is the first and most essential act of a species that intends to survive beyond its cradle. Acknowledging them is not pessimism, it is the deepest form of respect for the challenge and for the explorers who will face it. Each danger represents a frontier of knowledge waiting to be conquered. The solutions will not be found in a single breakthrough, but in a symphony of disciplines, from revolutionary materials science and closed-loop life support to advanced psychological support and ethical frameworks for genetic change. Our success as a spacefaring species will be measured not by the speed of our rockets, but by the depth of our preparation for the silent, slow-burn threats that wait in the void. Overcoming them will require the very best of our ingenuity, our courage, and our collective will. It transforms the dream of exploration from a simple act of departure into a profound testament to human resilience and adaptability. The journey to Mars or to the moons of the outer planets will be the hardest thing we have ever done, precisely because we will have chosen to do it with our eyes wide open to every conceivable risk. That conscious choice, that unwavering commitment to solving problems we can barely imagine today, is what will ultimately separate a fleeting adventure from the birth of a lasting interplanetary future. If you found this deep dive into the realities of space exploration compelling, consider subscribing. Together, we can continue to explore not just the wonders of the cosmos, but the fascinating, often hidden, human endeavors required to reach them.